Hi, now let's have a quick look at sparse files in Linux. We'll first check out what a sparse file is, then we look at ways to create sparse files and talk a little bit about converting files into sparse files and back, and we finish with a practical example. Now when you create a file in Linux, what actually happens is that in a directory data block an entry will be stored that has a name referencing to an inode in the file system. And this inode contains the properties of the file, like the size, the owner, the permissions, and more. And if you want to inspect those, of course you can use the ls command or the stat command, for example. But what's relevant for this discussion is that usually when you create a file with content, the inode will hold pointers to data blocks in the file system. The way the data is written to the file system is in blocks, obviously, which sizes may vary per file system. But in this example we see that 4K blocks are being used in the file system, and the file has a logical and physical size of 16 kilobytes, so 4 blocks. Now with commands like df and ls you can inspect the space usage of files in file systems, like this. So we have a file system mount point and we cd to that, and then we run df and it tells us that the file system has 2 kilobytes of space in use. And if we use dd to create a file of 16 kilobytes, we use def urandom as the input device, the block size is 16K, the count is 1 block, and the file name is going to be file1. Now df tells me that I use 19 kilobytes of total space in the file system. And ls tells me that 16 kilobytes is used for the file1. So the rest is overhead. So let's say file1 uses 16K logically as well as physically. Now a sparse file is a file like file1. It has a name as well as an inode, but the difference is that no actual blocks will be allocated. To easily create a sparse file you can use truncate like this. So I run truncate-s, specify the size of 16K, and the file name will be file2. Or we could use dd like this. We run dd, the input file will be /def urandom, the block size is 1, count is 0, so I'm not actually writing anything, but I'm going to set the end pointer to 16 kilobytes, and the name of the file is file3, but I'm not actually writing anything to disk other than the metadata of the file. And when we run ls again, we see that the logical sizes of all 3 files is 16 kilobytes. But with df we see that only one file has actually allocated 16K in the file system, next to some file system overhead of course. And a very nice option of the ls command is the sparse option. This will give you an additional column to list the actual space that a file uses. When we run that we see that the first column tells us that file 2 and file 3 have a physical space of 0, so no blocks in use for these 2 files. Now the thing about sparse files is that when you access them with applications or tools that do not understand sparse files, this will result in that such a tool will read all the metadata zeros, which aren't actually on disk, but if the tool then writes the file, the data will actually be written to the file on disk. So this means that this file is no longer sparse. So let's try that with VI. So I opened file2, which is a sparse file, in VI, and I see the representation of the null character, which is in fact the representation of zeros, which are not really on disk. So when we write the file and check with ls again, now we see that the file actually uses space on disk, and even a little bit more than file1. And if we want these zeros to be removed again, so to make it back into a sparse file, we can use fallocate. Now fallocate has quite a few options. Please look at the manual pages for yourself. But for this, the option -d is a handy one because we can dig holes in our file, meaning that it will release all the blocks that contain zeros. So we run fallocate-d and then the file name. And when we check with ls we see that the file has some overhead, but we've dropped back from 18 kilobytes to 2 kilobytes. Now the copy command has an option to deal with sparse files as well. So for example, I can create a file containing only zeros using dd. So I run dd, the input file is /def0, the output file is file4, the block size is 16 kilobytes and I want to create one single block. And so this will give me a file with a 16K worth of zeros. Now if we copy the file with the sparse option, we can either truncate or not. So we can say sparse equals always. That will free all blocks that contain zeros. So I copy file 4 to file 5, I say sparse is always, and then the actual size is back to nothing when we run ls again, of course. We could have used sparse equals never, but that would simply have copied all the blocks as they are. Finally, for a practical example, very often you use file systems to store particular types of data for special purposes. You should think of a data store for virtual machines or a file system to store backups as a replacement for tape units. What you can do is you can create a sparse file so it doesn't take any space actually, and put a file system on it and mount it. And then you will have a file system that really only uses the blocks when files are stored in the file system. So let's first clean up our current file system. So we remove all files, then we create a file of say 100 megabytes. So we truncate, specify 100 megabytes and call the file backup.img. The .img is just arbitrary. I could just have called it backup or whatever. It doesn't matter. Just the name of the file. Then we create a file system on it, running the make file system command. And then we check how much space the file system takes. And we see the logical space is 100 megabytes. But the physical space is only 334 kilobytes. So we know that the administration part of the file system takes this amount of physical space, and that's it. Now we loop mount it to /mnt backup. So we create a mount point first, and when we've done that, we mount the file system using a loop mount, right? So we loop mount the backup image to /mnt backup. Now let's copy our log files to the new file system by running a recursive copy of everything from var log into /mnt backup, which is our sparse file system. And when we run ls again, we see that the logical space is still 100 megabytes, but the physical space is only 9 megabytes. And that's it.